This tutorial is designed to understand the fundamental laws that govern chemical reactions. These laws are not mere assumptions or theoretical constructs. They are rooted in careful experimental observations and have stood the test of time. Regardless of how far chemistry advances or what new discoveries the future brings, these fundamental laws will continue to remain the foundation upon which our understanding of chemical reactions is built. So let's begin. Have you ever observed the transformation of matter? Every day, we see matter changing from one form to another. One of the most familiar examples is water. When ice is heated, it melts into liquid water. On further heating, the liquid water turns into water vapor. At first glance, these changes appear dramatic. A hard solid becomes a flowing liquid, and the liquid eventually becomes an invisible gas. If we look deeper at the molecular level, we find that the interactions between water molecules change significantly in each state. In ice, the molecules are tightly arranged. In liquid water, they move more freely. In water vapor, they are far apart and move almost independently. However, despite these changes, the identity of the molecule remains exactly the same. Whether it exists as ice, liquid water, or water vapor, the molecule is still H2O. Changes in which the chemical identity of a substance remains unchanged are called physical changes. But not all transformations of matter are physical. Sometimes, substances undergo much deeper changes in which entirely new substances are formed. The identity of the substance changes. Such transformations are known as chemical reactions. Then how and why does matter transform chemically? We shall start with a simple question. Why does iron rust? Why does wood burn? How is food digested? How are medicines produced? All of these involve chemical reactions. A chemical reaction is a process in which one or more substances are transformed into one or more new substances. For example, when hydrogen combines with oxygen, water molecules are formed. Here, hydrogen and oxygen disappear as separate substances and water is formed. It is important to note that, in a chemical reaction, the identity of elements does not change, they just rearrange to form new substances. Since chemical reactions arise from the intrinsic nature of elements, they, like all natural processes, are governed by certain fundamental laws. Scientists noticed that all chemical reactions follow certain rules. These observations led to 4 important laws. These are Law of Conservation of Mass, Law of Definite Proportions, Law of Multiple Proportions, and Law of Reciprocal Proportions. It is important to note that all these laws were established between 1789 to 1803, before the atomic theory proposed by Dalton in 1803. At this time, there was a very little understanding of atoms and other concepts such as valency and electrons. However, these laws were not based on theoretical assumptions, but on careful experimental observations. Therefore, they remain valid even today and known as the fundamental laws for the chemical reactions. Each law is a consequence of an attempt to solve a historical question. Therefore, we will discuss them one by one. First, coming to the law of conservation of mass. It was proposed by Antoine Lavoisier. Those days, the fundamental question was, when matter burns, where does it go? Does some of it disappear or become extinct completely? Before Lavoisier, many scientists believed in the phlogiston theory, which suggested that combustible substances released a mysterious substance during burning. Lavoisier carefully weighed reactants and the products in closed vessels after combustion. He found that the total mass before and after a reaction remained unchanged. Hence, he proposed an answer that became a fundamental law later. This law states that matter is neither created nor destroyed in a chemical reaction. They only change their form. Consider the neutralization reaction between sodium hydroxide and hydrochloric acid. Suppose we place a total of 1 gram of sodium hydroxide and hydrochloric acid in a closed reaction vessel. As the reaction proceeds, the amounts of NaOH and HCl gradually decrease, while the amounts of NaCl and H2O increase. However, at every instant during the reaction, the total mass of all the substances present inside the vessel remains 1 gram. This illustrates the law of conservation of mass. This showed that chemical reactions are rearrangements of matter, not creation or destruction of matter. Let's start with the second law, which is law of definite proportions. It was proposed by Joseph Proust. This law is derived from a question that, does a compound always contain its elements in the same proportion? To understand this in a modern context, consider citric acid. Is the citric acid extracted from a lemon chemically identical to the citric acid synthesized in a laboratory? If the answer is yes, then both samples must contain carbon, hydrogen, and oxygen in exactly the same mass ratio. Back then, Joseph Proust analyzed compounds obtained from different sources and prepared by different methods to answer this question. For example, Proust found that pure water always contains hydrogen and oxygen in the same fixed mass ratio, irrespective of its source. Whether the water is collected from a river, the sea, rain, or prepared in a laboratory, its chemical composition remains identical. Every pure sample of water consists of hydrogen and oxygen combined in a fixed mass ratio of 1:8. This law states that a compound always contains the same elements in the same mass ratio. This suggested that compounds are not random mixtures but have a definite composition of elements. Now, let us move on to the third law, the law of multiple proportions. This law was proposed by Dalton. The law of multiple proportions explains how the masses of two elements are related when they combine. It states that, when two elements combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in simple whole number ratios. Historically, chemists had been trying to understand the formation of different matter from the limited number of 118 elements. It gave rise to a fundamental question. Can the same two elements combine to form more than one compound? If they can, do they combine in any arbitrary proportion, or is there a hidden pattern? In the early 19th century, scientists discovered that carbon and oxygen can combine to form two different compounds such as carbon dioxide and carbon monoxide. So naturally one would expect that matters were continuous and the elements can combine in an arbitrary proportion. In that case, compounds like CO0.5, CO1.5, and C0.10 could exist in principle. But experiments showed a different picture. Chemists found that carbon and oxygen combine only in simple whole number ratios, giving compounds such as CO and CO2, but not arbitrary compositions like CO0.5 or CO1.5. This remarkable observation became the basis of the law of multiple proportions. Let us understand this law with a simple example. Suppose carbon and oxygen form only one compound. You find experimentally that 12 grams of carbon combines with 16 grams of oxygen. So the mass ratio is 12:16, which is 3:4. Now imagine they form another compound. This time you perform an experiment and found 12 grams of carbon combines with 32 grams of oxygen. Now ask yourself an important question. When the mass of carbon remains the same, which is 12 grams, how are the masses of oxygen related in the two compounds? In first compound it is 16 grams, and in second compound it is 32 grams. So the ratio becomes 1:2, which is a whole number ratio. In another reaction, 24 grams of oxygen is combined with 12 grams of carbon. Here, if we compare the mass of oxygen of the third compound with the first, then we will have a ratio of 2:3, which is again a whole number. Even if we compare with the mass of oxygen of the second compound, we will have a whole number ratio of 24:32 or 3:4. Now let's take an hypothetical reaction where 12 grams of carbon combines with 21.5 grams oxygen. If we compare the ratio of mass of oxygen with the first, then it will be 16:21.7, which is not a simple whole number ratio. So this compound does not exist. From these observations, Dalton concluded that whenever two elements combine to form more than one compound, the masses of one element that combine with a fixed mass of the other are always in simple whole number ratios. This statement is known as the law of multiple proportions. In this lecture, we will understand the law of reciprocal proportions. The law of reciprocal proportions is the most abstract of the four laws. The logic behind it is much more interesting. It began with a question that, if two elements separately combine with a third element to form separate compounds, is there any relationship between the amounts in which they combine with each other? From the observations, chemists found that there exists a strong relation, which gave rise to the law of reciprocal proportions. This law states that, if two different elements combine separately with the same weight of a third element, the ratio of the masses in which they do so are either the same or a simple multiple of the mass ratio in which they combine. We will understand this law with a simple example. Take hydrogen as the reference. If there are two other elements that separately combine with hydrogen to form their respective compounds, then experiments show that 8 grams of oxygen combines with 1 gram of hydrogen to form water, and 35.5 grams of chlorine combines with 1 gram of hydrogen to form hydrogen chloride. Here, both oxygen and chlorine combine with the same mass of hydrogen, which is 1 gram. The mass ratio of oxygen to chlorine is 8:35.5. As per law of reciprocal proportions, this ratio can be used to understand how oxygen combines with chlorine to form their compounds. Now, if chlorine combines with oxygen, it may form different compounds like Cl2O or ClO2. Here, this law says, the mass of chlorine that combines with the mass of oxygen to form a compound, their mass ratio must be same as 8:35.5, which is the mass ratio of these elements when they combines with fixed amount of hydrogen, or, after making the mass of one element the same, the mass of the other element will be in a simple whole number ratio. In Cl2O, the mass ratio of oxygen to chlorine is 16:71. Now, if we take the ratio of this mass ratio to the reference mass ratio, which is 8:35.5, then we will get 1:1, which is a whole number. And in ClO2, the mass ratio is 32:35.5. Here, the final ratio will be 1:4, which is simple whole number. Using the law of reciprocal proportions, chemists could predict the probable mass ratio in which two elements would combine with each other to form a compound, even if those two elements had never been observed to combine directly.